Welcome to Shanti-Peace for Mathematics. In this video, we are going to discuss regarding a spectrum of a self-adjoint operator. Before going for a spectrum of a self-adjoint operator, let us recall what we have did in our previous videos. For H, if we can have, it is a Hilbert space, and if you have a T which is a bounded linear operator, then we have defined a spectrum. A spectrum of T is defined as a set of all scalars such that T minus lambda I is not invertible. The Eigen spectrum is defined as a set of all scalars such that T minus lambda I is not 1, which is equivalent to saying that the kernel is not 0, which is also says that there exists some element x which is in H such that norm of x is 1 such that T minus lambda Ix is 0. Then we have defined the approximate eigen spectrum, which is defined as set of all scalars such that T minus lambda I is not bounded below. So it is approximate eigen spectrum, so that's why there is a sequence xn belongs to H with norm 1 such that T minus lambda I xn is tending to 0. That is another way is to represent the same definition. Then we have discussed certain results regarding this spectrum. The first result which we have seen that if lambda is belongs to a spectrum of T, if and only if its conjugate it belongs to a spectrum of adjoint of the operator. Then we have discussed this relation between this eigenspectrum, approximate eigenspectrum, and a spectrum of. The relation is look like this, so that eigenspectrum is a subset of approximate eigenspectrum, which is a subset of a spectrum of T. A spectrum of T having this relation, that means spectrum of T is equal to approximate eigenspectrum union this. Then we have seen some results for a normal operator. So that means a spectrum of a normal operator. As we know that the normal operators are those operators which having satisfying this condition, that means T star T is equal to T star, where T star represent the adjoint of T. And in that the first result which we have discussed is lambda is belongs to eigen spectrum of T if and only if lambda conjugate is belongs to eigen spectrum of T star. This is the first result. If T is normal, then approximate eigen spectrum of T will be same as a spectrum of T. That is another result we have discussed in my previous video. Then we have seen that if you have a two eigenvalues, that is lambda 1 and mu belongs to the eigen spectrum of T, and if lambda and mu are not same, and corresponding to this lambda there is an eigenvalue, eigenvector, that is T x is equal to lambda x and T y is equal to mu y. So corresponding to lambda there is x is eigenvector, and corresponding to mu there is y is eigenvector. Then, and these two are different, then x is perpendicular to y. So this condition implies that x and y are orthogonal. After discussing this spectrum of a normal operator, we have discussed certain more results on numerical range. A numerical range is defined or denoted by Wt, which is a set of all scalars each is of the form Txx, inner product of Txx, such that x belongs to H with norm of x is equal to 1. So numerical range is defined like this, and we have seen the first result on this numerical range is always bounded set, and it is bounded by norm of T. That means it's also bounded function at bounded set, and that set is always bounded by norm T. The second result we have discussed is lambda is belongs to numerical range of T if and only if lambda conjugate is belongs to numerical range of T star, as we have result for the same as the spectrum which we have here also. Then we have discussed that the eigen spectrum is always a subset of a numerical range of T. The fourth result that we have discussed is approximate eigenspectrum is a subset of closure of numerical range of T. The next result that we have discussed is a spectrum is also a subset of numerical range of T closure. So these are the results which we have discussed for a numerical range, spectrum, and all sort of relation normal operator. Now in this lecture, we are discussing a spectrum of self-adjoint operator. As we know that the self-adjoint operator are the generalization of a symmetric matrix, and the definition of a self-adjoint operator is adjoint itself. So the first result that we can observe for this self-adjoint operator is numerical range of T is always a subset of a real line. And this can be seen in this fashion. Let us consider lambda is belongs to numerical range of T. If lambda is belongs to numerical range of T, as per the definition, there exists x belongs to H with norm of x is 1 such that lambda is equal to Txx. If I use the definition of adjoint, I can rewrite this as x T star x by taking this T here and applying the definition of adjoint. We can have this T is a self-adjoint, so it is x Tx we have. If you can interchange, this is Txx, so you will have this, and this will be the T lambda conjugate. So hence what we have, it is lambda is same as lambda conjugate, which is only happen if the value of lambda is a real number. So that means lambda is belongs to real line. So that's why we can say that this numerical range is always a subset of real line. Since we have a numerical range which is a subset of a real line, we also can say that a spectrum of T is also a subset of a real line, because as we know that the spectrum is always subset of a closure of this, and since numerical range is a subset of a real line, its closure is also a subset of a real line, so this is also a subset of R. And if you can see as a matrix, if you have a symmetric matrix, then we know that the eigenvalues of symmetric matrix are always a real number. And with the same concept we have generalized for the self-adjoint operator, we can have the same results here. Now there are some notations I am following for throughout this lecture. So the notation that I am considering, that let T belongs to BL of H where T is a self-adjoint, and consider this two notation, that is small mt, which I am saying it is a infimum of set of all lambda such that lambda belongs to numerical range of T. Capital M of T is supremum of set of all lambda such that lambda belongs to numerical range of T. So these are the two definition. It is always exist. I am taking as a note here because numerical range is always a bounded subset of R. Since it is a self-adjoint, it is a subset of R, and for any operator, this numerical range is bounded by its norm that we already have proved. So this small mt and capital MT is always exist. And we can talk about its supremum and its supremum of all values which are having this. Now let us have first result on here, which tells you that let H be a Hilbert space which is non-zero. I'm considering it is a non-zero Hilbert space, and T belongs to BLH, which is a self-adjoint operator. Then prove that the small T and capital MT, that is infimum and supremum of numerical range, is belongs to the approximate Eigen spectrum of T. And for normal operator, we already have proved that the approximate Eigen spectrum and spectrum of T are same. So this spectrum of T is subset of small mt and capital MT. That is interval small mt to capital MT. That means the spectrum is also bounded by this interval. So let us try to prove this statement. See, what is the definition of MT we have? It is an infimum of set of all values lambda such that lambda is belongs to numerical range of T. Since it is an infimum and lambda belongs to this, therefore there exists some sequence xn belongs to H with norm of xn is equal to 1 such that there is a sequence in this, that means xn converges to MT, because every element of this numerical range is look like this. I can say that there exists a sequence lambda n belongs to Wt such that Wn is tends to. So as per that definition of infimum, we can have such sequence, and we already can note here that as is self-adjoint, it is easily see that T minus lambda I is also self-adjoint. You can see that T minus lambda I star will be T star minus lambda conjugate I star. Lambda conjugate is always same because it is a real number. So that is lambda star minus lambda I star, and since T is a self-adjoint, lambda T star will be same as T, so that is T minus lambda I. So that's why if T is self-adjoint, T minus lambda I is also self-adjoint for lambda belongs to R. So I can say that T minus MTI is also self-adjoint in particular because MT is a real number and we have this. So now for all x belongs to H with norm x is equal to 1, I can start with this T minus MTI xx. By applying the definition of linear operator and inner product, we can write down this is as Txx minus MTxx. But a norm of x is 1, so this quantity will gives me 1. So this is equivalent to write down is Txx minus MT. And this MT is the infimum of whatever the value which we have in the numerical range, and this is also in numerical range. So this value is always greater than or equal to 0. So that means I can say that T minus MTI xx is greater than or equal to 0 for all x with having this situation. So therefore I can say that T minus MTI xx is greater than or equal to 0 for all x belongs to H with norm of x is 1, and T minus MTI is self-adjoint. So I can say that T minus MTI is positive operator. That is the definition of a positive operator. I can say that T minus MTI greater than or equal to 0. By taking S, I'm taking S is equal to T minus MTI, and I want to apply the generalized squares inequality. So let us recall what is this generalized squares inequality says. So this is the statement is known as generalized squares inequality, which tells you that let H be a Hilbert space and S belongs to BLH. S or minus S is positive if and only if mode of SXY inner product of this less than or equal to square less than or equal to inner product of Sx into inner product of Syy. This is the theorem which is known as the generalized squares inequality, and I want to apply this theorem for this S, and we already have proved that this is a positive operator. So T minus lambda I is positive operator. So applying this generalized squares inequality on this, so I just write that by generalized class inequality. Inner product of xy, mode of inner product of xy square is less than or equal to inner product of sx, inner product of sy y for every x and y belongs to h. This is true. Now by taking x is equal to xn and y equal to sxn, replace here with this values. So if we can see that what is this quantity, that is sxn, instead of y I have to substitute this. This is sxn, inner mode of that square is equal to, on the other side we have sxn xn, instead of x I have to put xn, instead of y I have to put sxn, so this is x square xn sxn. Now this quantity is nothing but the norm of sxn and square is there, so it is norm of sxn power 4. This is less than or equal to, we have here, which is less than or equal to, this is sxn xn as it is. This quantity is write as less than or equal to norm of xn square, norm of xn. And since s is a self-adjoint operator, I just write this as further as norm of s xn power 4 is less than or equal to s xn xn as it is. This quantity is further I can write down less than or equal to norm of s cube, because as it is the self-adjoint operator, norm of s square, which is the same as norm of s whole square. So it is norm of s square and norm of s will together with the norm of s whole cube, and as a norm of xn is equal to 1 will gives me this. Now let us observe what is this quantity. This is sxn xn, which is t minus mti xn xn, because we already have seen that what is s we have taken as t minus mti, so that is the value we have here. Now this is nothing but the t xn xn minus mt, and this will tends to 0 as xn is tending to mt, as we already have seen that here. We have taken that sequence of xn such that we have t xn is tending to mt. So due to this quantity which we have here, xtn, so x s xn xn is tending to 0. That means this quantity which we have here from this equation 1 or inequality 1, from inequality 1 we have norm of xn power 4 is tending to 0. So therefore this will gives you xn tends to 0. But xn tends to 0 as the value of s we have minus mti xn will tends to 0. But this will suggest you that mt is belongs to approximate eigen spectrum of T. In similar manner, can prove that capital MT is also belongs to approximate eigen spectrum of T. So thus what we can have is small mt and capital MT is both of them is belongs to approximate eigen spectrum of T. To prove this statement you required minus s is positive. Instead of, in the proof we have used s is equal to t minus mt I. So this is my s, and here to prove this one we required minus s is positive. Since this is approximate eigen spectrum of T is same as spectrum of T, these two are equal, and this will be the subset of numerical range closer and numerical range is bounded by this two, so that's why this will be the subset of capital MT and small mt. It is interval. The spectrum is real and is bounded by this two, bounded by this interval. Now let us have another result for this self-adjoint operator. It's saying that let H be a Hilbert space and belongs to BL of H, self-adjoint. Then first one is norm of T. We can calculate using this numerical range, which is saying that maximum of small t and capital T. So either it is this norm T is either a small t or a capital T, or I can say it is a supremum of mode of lambda, where lambda is belongs to spectrum of T. Here is also we have a mode. Second result is saying that norm of T, which we can have, it is a supremum of norm of or mode of T by 2, which is the square root of this spectrum of T star T. Let us try to prove the first statement here, and the proof is very small and straightforward. We already have proved that small t and capital T belongs to approximate eigenspectrum of T, and approximate eigenspectrum is same as spectrum of T for the normal operator, since it is self-adjoint, which is also true, and which is a subset of a numerical range closure for any operator, and this will be the subset of a small t and capital T, capital MT. So this is the result which we already have. Now we already know that a norm of T for the bounded linear operator is defined as supremum of x Tx such that x belongs to H with norm of x is 1. So if T is self-adjoint, then the norm is defined like this, which we already have. But supremum of this one is nothing but this definition is nothing but the supremum of the values which is in numerical range of T. But the numerical range of T, that means the supremum is either small mt, mode of small mt, or it is a capital MT. So hence it is a supremum of modulus of lambda belongs to spectrum of T. So the norm is defined like this. Now the second result that we have it is T is a self-adjoint operator, which we have. So that's why norm of T square, which is same as T star T. So by this result which we have here, the norm of T star T by this way, by this one, what we can say is a supremum of lambda such that lambda belongs to a spectrum of T star T. But due to this result, this quantity is nothing but the norm of T square norm. So by taking a square root, what we can have, it is norm of T is nothing but the supremum of square root of lambda mode of mode lambda such that lambda is belongs to spectrum of T star T. So by this one line proof, which we can have this statement. Now in this self-adjoint operator, we have a last result, which is the known as Riesd method. See what is this Riesd method is. Let H be a space, H is not equal to 0, and T is belongs to BL of H, self-adjoint. Consider x1, x2 up to so on, they are belongs to H. Then for n is running from 1 to up to so on, let us consider Yn, which is a linear span of a finite element, that is x1, x2 up to xn. Let us take alpha n is infimum of pxx such that x belongs to yn with norm of x is equal to 1. Beta n is supremum of pxx such that x belongs to yn with norm of x is equal to 1. Then prove that this small mt is less than or equal to alpha n plus 1 is less than or equal to alpha n up to so on. That is also less than or equal to alpha 1 less than or equal to beta 1 less than or equal to beta 2 up to so on. Beta n less than or equal to beta n plus 1, which is less than or equal to capital MT. So all this value which we having this numerical range of in this lambda n range of t with the domain yn, we have this. And also if this linear span x1, x2 up to so on is dense in H, then this small mt is nothing but the limit of lambda n as n tends to infinity. That means lambda n, say this alpha n is converged to small mt, and beta n, which we have, it is a supremum of this value, is converged to capital MT. So this is the statement for this Rees method, which tells you that if you have this finite linear span of elements of H, and if you define alpha n and beta n in this manner, then they are satisfying this inequalities. And if this linear span for all this elements which is dense in H, then this alpha n is converged to small mt and beta n is converged to capital MT. Let us try to prove this statement. So once we can observe here is yn is a linear span of x1, x2 up to xn. Yn plus 1 is always a superset of yn. This is the first thing we can note. And once we have this one, it is clear that this alpha n, we have this alpha n is a non-increasing and it is bounded by mt. So if this is there, then we have this relation mt is less than or equal to small n plus 1 less than or equal to alpha n up to so on less than or equal to alpha 1. This is we already have, and then alpha 1 is less than or equal to beta 1 is less than or equal to capital MT, because it is just by the definition of a supremum and infimum we have this relation. And we can note that this alpha n is a non-increasing sequence and which is a bounded below. And if the sequence which is non-increasing and it is a bounded below, then it must converge. So therefore I can say that alpha n is converged. Since it is converged, let us consider alpha n is converged to m0. Let us say it is converged to m0. Now it is clear that this small mt, which we have infimum of values which are in numerical range, and this m0 is converged to, and alpha n is some finite value. So it is clear that this m0 is always bigger than this small mt, which is clear. Now we need to prove that the reverse side. That means I need to prove that what is our objective is to prove m0 is less than or equal to small mt. Suppose not, this is not possible. So what we can assume is, suppose if possible, small mt is less than m0. Therefore there exists x belongs to H with norm of x is 1 such that there is some value in numerical range So that means mt is less than inner product of tx x, which is less than m0. Now this linear span of this x1 x2 up to so on is dense in H. There exists some sequence, let's say yn, belongs to this linear span of x1 x2 up to so on, such that yn is converse to x in H. Now what is the norm of yn? Is nothing but is tending to norm of x, but norm of x is 1. For sufficiently large n, for large n, let's consider Zn is yn upon norm yn. Now we just observe that this Zn is norm of Zn is 1 and Zn is tends to x because of norm of x is 1. As this yn is belongs to linear span of x1 x2 up to so on, there exists some integer jn such that yn is belongs to yjn. Yjn is nothing but the linear span of x1 x2 up to xn xj n. Therefore this Zn is actually belongs to this yjn, and by taking a limit, what we have is m0, which is less than or equal to alpha jn. What is alpha jn? Is the infimum of alpha n is definition is infimum of txx. So this is the infimum, and m0 is the limit of alpha n, that is less than or equal to inner product of t zn zn, and which is tending to txx because Zn is tends to x, so t Zn is tends to tx, so inner product is also tends to, and that is less than or equal to m0, and which gives you a contradiction that m0 is less than strictly, this is strictly less than m0, and which will gives you a contradiction with the m0 is strictly less than m0, and hence we can have is mt is equal to m0, which is same as limit of alpha n as n tends to infinity. So in same way we can just see that we can observe that this beta n is a non-decreasing bounded above sequence because it is a supremum, and we have yn is the linear span of x1 x2 up to xn. If you add one more point, it will be increased than that. So obviously it is a non-decreasing sequence of bounded above, and it is bounded above by capital MT, and hence it is convergent. And since it is a convergent, in similar way we can say that this it's converged to this capital MT, and that's complete the proof of Rees method. So in this lecture we have discussed the spectrum of a self-adjoint operator, in which we have seen that a spectrum of a self-adjoint operator is always bounded, and it is bounded by interval with the supremum and the infimum of value of a numerical range. That's it for this video. If you like this video, please subscribe, like, and do comment below. Thank you. See you. Bye bye. Sayonara.